The Fibonacci sequence is a series of numbers with a simple rule. You start with 0 and 1. Then each number is the sum of the two before it, so it goes 0, 1, 1, 2, 3, 5, 8, 13, and so on. This sequence, named after the Italian mathematician Leonardo of Pisa, known as Fibonacci, has fascinated mathematicians, scientists, and artists for centuries. The sequence was first introduced in Fibonacci's book Liber Abaci in 1202. Fibonacci posed a problem about rabbit population growth, and the solution led to this fascinating sequence. Little did he know that this sequence would have profound implications in various fields, far beyond the realm of simple rabbit populations. The Fibonacci sequence is more than just a mathematical curiosity. It appears in surprising and beautiful ways in the natural world. From the arrangement of petals in a flower to the spiral patterns in a seashell, the Fibonacci sequence is evident in the very fabric of nature. This essay will delve into the captivating world of the Fibonacci sequence, exploring its mathematical properties, its ubiquitous presence in nature, and its profound influence on art, architecture, music, and even computer science. Join us on this journey as we unravel the mysteries and marvel at the elegance of this extraordinary numerical sequence. The Fibonacci sequence can be defined mathematically using a recursive formula. This means that each term in the sequence is defined in terms of the preceding terms. The formula is as follows. F of n equals f of n minus 1 plus f of n minus 2, where f of n is the nth term in the sequence, f of n minus 1 is the n1th term in the sequence, and f of n minus 2 is the n2th term in the sequence. This formula simply states that to find any Fibonacci number, you just add the previous two Fibonacci numbers. For example, to find the 6th Fibonacci number, you add the 5th Fibonacci number, which is 3, and the 4th Fibonacci number, which is 2, resulting in 5. Another fascinating aspect of the Fibonacci sequence is its connection to the golden ratio, often represented by the Greek letter phi. As you go further down the Fibonacci sequence, the ratio between consecutive numbers gets closer and closer to the golden ratio, which is approximately 1.618. This relationship between the Fibonacci sequence and the golden ratio is not just a mathematical coincidence. It has profound implications for the aesthetic qualities of art, architecture, and even natural forms. We will explore these connections in more detail in the following sections. The golden ratio, often represented by the Greek letter phi, is an irrational number approximately equal to 1.618. It's been a subject of fascination for mathematicians, artists, and architects for centuries due to its unique mathematical properties and its aesthetically pleasing proportions. The connection between the Fibonacci sequence and the golden ratio is truly remarkable. As you go further down the Fibonacci sequence and divide a number by its predecessor, the result gets closer and closer to the golden ratio. For example, 1 divided by 1 equals 1, 2 divided by 1 equals 2, 3 divided by 2 equals 1.5, 5 divided by 3 equals 1.666, 8 divided by 5 equals 1.6, 13 divided by 8 equals 1.625, and 21 divided by 13 equals 1.615. As you can see, the ratio oscillates around the golden ratio, getting closer with each successive term. This convergence to the golden ratio is a testament to the intricate relationship between these two mathematical concepts. The golden ratio is often used in art and architecture to create visually pleasing proportions. The ancient Greeks believed that the golden ratio created a sense of harmony and balance in their structures, and they incorporated it into many of their buildings, including the Parthenon. The use of the golden ratio in art and architecture continues to this day, as artists and architects strive to create works that are both aesthetically pleasing and mathematically elegant. The Fibonacci sequence exhibits fascinating divisibility properties that have intrigued mathematicians for centuries. These properties are not just mathematical curiosities. They reveal a deeper structure and interconnectedness within the sequence. Here are a few key divisibility properties. Every third Fibonacci number is even. This is because the sum of two odd numbers, the previous two Fibonacci numbers, is always even. Every fourth Fibonacci number is divisible by 3. This pattern emerges because each Fibonacci number is the sum of the previous two, and the cycle of remainders when dividing by 3 repeats. Every fifth Fibonacci number is divisible by 5. Similar to the divisibility by 3, this property arises from the repeating cycle of remainders when dividing Fibonacci numbers by 5. These patterns continue for higher divisors, revealing a hidden order within the seemingly simple Fibonacci sequence. These divisibility properties are not just interesting mathematical quirks. They have implications for understanding the structure of the Fibonacci sequence and its relationship to other mathematical concepts. The study of these divisibility properties has led to a deeper understanding of the Fibonacci sequence and has even found applications in areas such as cryptography and computer science. These properties are a testament to the rich and often unexpected connections that exist within the world of mathematics. Section 5. The Fibonacci sequence in nature. The Fibonacci sequence is not just confined to the realm of mathematics. It manifests itself in surprising and beautiful ways in the natural world. From the arrangement of petals in a flower to the spiral patterns in a seashell, the Fibonacci sequence is evident in the very fabric of nature, revealing a hidden mathematical order within the seemingly random patterns of the natural world. One of the most striking examples of the Fibonacci sequence in nature is the arrangement of seeds in a sunflower head. The seeds are arranged in 2 sets of spirals, one clockwise and one counterclockwise. The number of spirals in each set is almost always a Fibonacci number. For example, a sunflower might have 34 spirals in one direction and 55 in the other, both Fibonacci numbers. The Fibonacci sequence also appears in the arrangement of leaves on a stem, known as phyllotaxis. Plants have evolved to arrange their leaves in a way that optimizes sunlight exposure. By following the Fibonacci sequence, leaves can be spaced out in a way that minimizes shading of lower leaves, allowing for maximum sunlight absorption. The Fibonacci spiral, a logarithmic spiral that grows outward by the golden ratio with each quarter turn, is also found in nature. The chambers of a nautilus shell, for example, are arranged in a Fibonacci spiral. As the nautilus grows, it adds new chambers, and the spiral shape allows it to maintain its proportional shape throughout its life. The prevalence of the Fibonacci sequence and the golden ratio in nature is not a coincidence. These mathematical concepts provide efficient and elegant solutions to problems that organisms face in their growth and development. The Fibonacci sequence is a testament to the power of mathematics to explain and predict the patterns we observe in the natural world. Section 6. The Fibonacci sequence in art and architecture. The Fibonacci sequence and the golden ratio have been used in art and architecture for centuries to create aesthetically pleasing and harmonious proportions. From ancient Greek temples to Renaissance paintings to modern sculptures, these mathematical concepts have had a profound influence on the visual arts, shaping our perception of beauty and balance. One of the most famous examples of the golden ratio in architecture is the Parthenon. The ancient Greeks believed that the golden ratio created a sense of harmony and balance, and they incorporated it into many of their buildings, including the Parthenon. The dimensions of the Parthenon, the placement of its columns, and even the proportions of its sculptures all exhibit the golden ratio, creating a sense of visual harmony that has captivated viewers for centuries. During the Renaissance, artists rediscovered the golden ratio and used it extensively in their paintings and sculptures. Leonardo da Vinci, for example, used the golden ratio to create the perfect human proportions in his famous drawing Vitruvian Man. The golden ratio is also evident in the composition of many Renaissance paintings, such as Michelangelo's The Creation of Adam on the ceiling of the Sistine Chapel. The use of the Fibonacci sequence and the golden ratio in art and architecture continues to this day. Modern artists and architects are still fascinated by the aesthetic qualities of these mathematical concepts, and they continue to explore new and innovative ways to incorporate them into their work. The enduring appeal of the Fibonacci sequence and the golden ratio in the arts is a testament to their timeless beauty and their ability to evoke a sense of harmony and balance. Section 7. The Fibonacci sequence in music. The influence of the Fibonacci sequence extends beyond the visual arts and into the realm of music, where it manifests in the structure of musical scales, the arrangement of musical sections, and even the duration of notes, creating a sense of natural flow and balance in musical compositions. The diatonic scale, a fundamental element of Western music, exhibits Fibonacci relationships. The octave, a musical interval spanning 8 notes, can be divided into sections of 5 and 3 notes, both Fibonacci numbers. The major and minor scales, the building blocks of Western musical harmony, also exhibit Fibonacci relationships in their interval patterns. Composers throughout history have incorporated Fibonacci numbers into their music, often subconsciously, to create aesthetically pleasing proportions. For example, Mozart's Sonata No. 1 in C major exhibits Fibonacci relationships in the arrangement of its musical phrases. The first movement is divided into sections of 32, 20, and 12 measures, all close approximations of Fibonacci numbers. The Fibonacci sequence also appears in the rhythmic structure of music. Some composers have experimented with using Fibonacci numbers to determine the duration of notes and rests, creating rhythmic patterns that are both complex and strangely satisfying. The Fibonacci sequence provides a framework for creating musical structures that feel balanced and natural, even when they are mathematically complex. The use of the Fibonacci sequence in music is not limited to Western classical music. It can be found in various musical traditions around the world, suggesting that its appeal is universal and deeply rooted in our perception of sound and rhythm. Whether consciously employed or intuitively felt, the Fibonacci sequence continues to influence the creation and appreciation of music, adding a layer of mathematical elegance to the art form. Section 8. The Fibonacci sequence in computer science. The Fibonacci sequence, with its elegant recursive nature, has found numerous applications in computer science, particularly in the design of algorithms and data structures. Its properties make it a valuable tool for solving computational problems efficiently and elegantly. One of the most well-known applications of the Fibonacci sequence in computer science is in the Fibonacci heap data structure. A Fibonacci heap is a type of priority queue, a data structure that allows for efficient retrieval of the minimum or maximum element. Fibonacci heaps use Fibonacci numbers to maintain their structure, enabling them to perform operations like insertion, deletion, and finding the minimum element in amortized constant time, making them suitable for applications where efficiency is paramount. The Fibonacci sequence also plays a crucial role in the analysis of algorithms. The time complexity of some algorithms, such as the Euclidean algorithm for finding the greatest common divisor of two numbers, can be expressed in terms of Fibonacci numbers. Understanding these relationships helps computer scientists analyze and optimize the performance of algorithms, making them run faster and more efficiently. Furthermore, the Fibonacci sequence has applications in cryptography. The sequence's unique mathematical properties make it suitable for generating pseudo-random number sequences, which are used in various cryptographic applications, such as generating keys and encrypting data. The Fibonacci sequence's versatility and elegance make it a valuable tool in computer science. Its applications in data structures, algorithm analysis, and cryptography highlight the practical implications of this seemingly simple mathematical concept in the digital age. As computer science continues to evolve, the Fibonacci sequence will likely find even more applications in solving complex computational problems. Section 9. Modern applications of the Fibonacci sequence. The Fibonacci sequence, far from being a relic of ancient mathematics, continues to find new and unexpected applications in various fields, demonstrating its enduring relevance in the 21st century. From predicting financial markets to optimizing the design of antennas, the Fibonacci sequence is proving to be a versatile tool for solving modern-day problems. One intriguing application of the Fibonacci sequence is in financial market analysis. Traders use Fibonacci retracement levels, which are derived from the golden ratio, to identify potential support and resistance levels for stock prices. These levels are believed to represent points where the market is likely to reverse or consolidate. While the effectiveness of Fibonacci retracement in financial trading is debated, it remains a popular tool among technical analysts. The Fibonacci sequence has also found applications in antenna design. Engineers have discovered that antennas based on Fibonacci spirals exhibit desirable radiation patterns, making them suitable for use in wireless communication systems. These antennas can be made compact while still maintaining high performance, making them ideal for use in mobile devices and other applications where space is limited. In the field of optimization, the Fibonacci search technique utilizes the golden ratio to efficiently find the extremum, minimum or maximum of a unimodal function, a function that has only one peak or valley. This technique is used in various applications, such as tuning the parameters of a machine learning model or finding the optimal solution to an engineering problem. The diverse applications of the Fibonacci sequence in fields as varied as finance, engineering, and computer science highlight its enduring relevance and its ability to solve real-world problems. As our understanding of this fascinating sequence deepens, we can expect to see even more innovative applications emerge in the future. Section 10. The enduring impact of the Fibonacci sequence. The Fibonacci sequence, a seemingly simple mathematical concept, has captivated mathematicians, scientists, artists, and musicians for centuries. Its enduring impact stems from its unique mathematical properties, its ubiquitous presence in nature, and its ability to evoke a sense of beauty, harmony, and balance. The Fibonacci sequence's influence can be felt in various fields. It has inspired artists to create masterpieces of visual art, architects to design awe-inspiring structures, and musicians to compose soul-stirring melodies. Its presence in nature, from the arrangement of petals in a flower to the spiral patterns in a seashell, reveals a hidden mathematical order within the seemingly random patterns of the natural world. In the realm of science, the Fibonacci sequence has found applications in computer science, physics, and even financial market analysis, demonstrating its versatility and its ability to solve real-world problems. Its enduring relevance in the 21st century is a testament to the power of mathematics to explain and predict the world around us. The Fibonacci sequence is more than just a mathematical curiosity. It is a fundamental principle that underlies many aspects of our world, from the smallest seed to the vast spiral galaxies. Its study continues to inspire new discoveries and applications, ensuring that its influence will continue to be felt for generations to come. Section 11, Conclusion: The Fibonacci sequence, a timeless wonder. The Fibonacci sequence, with its simple yet profound nature, stands as a testament to the elegance and interconnectedness of mathematics, nature, and human creativity. Its presence can be seen in the delicate petals of a flower, heard in the harmonious melodies of a Mozart sonata, and felt in the awe-inspiring grandeur of the Parthenon. As we have explored its mathematical properties, its manifestations in nature, and its influence on art, architecture, music, and even computer science, we have only scratched the surface of the mysteries and wonders that the Fibonacci sequence holds. Its study continues to inspire new discoveries and applications, ensuring that its legacy will endure for generations to come. The Fibonacci sequence serves as a reminder that mathematics is not merely a dry and abstract subject, but rather a language that describes the very fabric of our universe. It is a language of beauty, harmony, and order, and its study can lead to a deeper appreciation for the intricate connections that bind all things together. In the words of the great mathematician Johannes Kepler, geometry has two great treasures. One is the theorem of Pythagoras, the other the division of a line into extreme and mean ratio. The first we may compare to a measure of gold, the second we may name a precious jewel. The Fibonacci sequence, intricately linked to the golden ratio, embodies this precious jewel, reflecting the beauty and elegance of the universe itself.